Hello everyone, welcome back again to my channel. In this tutorial I will try to explain how to simulate the pile draft foundation with PLAXIS 2D using a plane strain approach or plane strain model. So let us begin. This is our example of a pile draft foundation. It contains of a raft and a group of piles. So the raft foundation is 7 meter wide and 13 meter in length. Also there's a group of piles uh, which are 3 by 6, about 18 piles, and the thickness of the raft is 0.5 meter, and the diameter of the pile is 0.5 meter as well. Also the length of the pile is 15 meters. So as you see, this is our example, and to model this pile draft foundation in PLAXIS 2D, we have to change it to the plane strain model. The primary challenge encountered when applying a plane strain model to simulate a pile draft foundation or any other structure is the shift from three-dimensional to two-dimensional representation. Necessitating the conversion of a three-dimensional scenario into a two-dimensional model. So this conversion entails simplifying the out of plane rows of piles into a wall element. So this is referred as a plane strain piles. So in this example, we will try to convert this rows of piles into an equivalent plane strain wall. As we see in here, I modeled a simple 3D model to make it better understandable. So this is our pile draft foundation, and in plane strain model we have to convert this three-dimensional into this two-dimensional plane strain model. Also in PLAXIS or in plane strain model, we will just consider 1 meter of this model. For example, this raft is 13 meter long, so we will consider just 1 meter length of the raft. So to convert these rows of the pile to equivalent plate wall, we have to do some changes. For example, the wall element is specified as I mentioned before. The wall element is specified on a per meter basis, meaning that the normal stiffness EA, modulus of elasticity and area, also the bending stiffness and weight attribute to the pile in the rows outside of the plane are distributed or smeared over each meter length of the wall element. For example, if you want to change the stiffness properties of this rows of the pile to the equivalent plane strain wall, for example, the normal stiffness of plane strain of equivalent equal the normal stiffness of each pile times the number of the pile in the row, the number of the pile in this row. In our example we have 6 piles, divided by length of the raft out of the plane, in this case, which is equal 13 meter. Also the bending stiffness of the plane strain of equivalent equal the bending stiffness of each pile times the number of the pile in the row divided by length of the raft in out of the plane. Also, similar to the normal stiffness and bending stiffness, the weight of the plane strain of the wall of equivalent equal weight of the pile per meter times the number of the pile in the row divided by length of the raft out of the plane. So changing the three-dimensional pile raft foundation to the plane strain model also affected the frictional resistance of the pile shaft. So these formula are suggested by the literature to be used during simulating the pile raft foundation using a plane strain model. So in PLAXIS we generally use this factor R inter, which is the interface reduction factor. We make an interface. We make an interface between the soil and any other structure like a pile or wall. So in this formula, R inter of the plane strain or equivalent plane strain equal number of piles in the row times the surface area of the each pile times the R inter of each pile divided by 2LR. 2LR it means because the friction happens on both sides of the wall. So to convert the three-dimensional pile raft foundation to a plane strain model, first we will talk about the properties of the raft foundation. So as we said, the raft is the reinforced concrete. So the unit weight of the concrete is 25 and the modulus of elasticity is 3 times 10 to power 7 kilonewton per square meter, and the void ratio is 0.2, and area of the plate or area of the raft. So as we said, we will just simulate 1 meter of the raft. So it is equal B times H. H is the thickness of the raft, which is 0.5, and B we take 1 meter, as we said, because we are using the plane strain model. So the moment of inertia, area moment of inertia equal H to power 3 times B divided by 12. Also by calculating the area and moment of inertia of the plate, we calculate the normal stiffness and bending stiffness of the plate. So these parameters will be used in PLAXIS. Also the weight of the raft should be calculated in per meter. So it is equal unit weight of concrete times the thickness of the raft times length of the raft, which we take 1 meter. For piles in plane strain model, so it's also the reinforced concrete. It has they have the same properties as the raft foundation. Area of the pile equal pi d square over 4. Also the moment of inertia of the pile, which is circular, is equal pi d to power 4 divided by 64. Diameter of the pile is equal 0.5 and length of the pile is equal 15 meter. So the normal stiffness of the plane strain of equivalent equal this formula as we talked about before, and we calculated as 2.719 times 10 to power 6, and also bending stiffness was calculated, and weight of the plane strain equivalent also calculated like this. So these are the simple calculation. You can calculate it very easily. And for interface reduction factor, So many researchers and literature suggest that this formula shouldn't be used because using plane strain model for pilot foundation generally overestimate the settlement. So we take our interface reduction factor equals 0.8 for concrete in this example. If you calculate by this formula, it will become 0.3. So if you want, you can do both. You can use both of them and see the result. What happens when you use 0.8 for interface and when you use 0.3. So we go to the PLAXIS. This is our model in the PLAXIS 2D. So at first we have to define the soil geometry. So we defined the big soil contours to minimize the effect of boundary condition or on the results of the model. As you say in here, we go to file in project properties. The model we use is a plane strain model. Also we use 15 noded element mesh. As I said, we use a big contour model to minimize the effect of boundary on the numerical results. Also the soil height is 40 meters and it contains of two sandy soil layer. So after defining the soil geometry, we have to define the borehole, create borehole. So we defined it before. This is the borehole. So it contains of two soil layer. The first one is 10 meter and the second one is 30 meters. So the water is located at 3.5 meters below the ground level, and also I want to show you the properties of each soil material. So in the upper soil layer we use the medium dense soil. These are the properties of the soil, the unit weight and saturated unit weight. Also we used the Mohr column model as a constitutive model and the drain condition. The shear strength parameter also are used in here. You can see it, the elasticity and Poisson ratio and cohesion and internal friction angle. Also the interface, as I mentioned before, we use 0.8 for both soils. Also this is the dense sand soil layer. We also use the Mohr column model, and these are the unit weight of unsaturated and saturated unit weight. Also these are the shear strength properties of the soil, and the interface 0.8 was used as an upper layer. So after defining the soil geometry and boreholes and defining the soil material for the first layer and the second layer and assigning the soil material to the borehole, then we proceed to the structure. So in structure mode we define the raft as a plate. In here we can go to the create line and create plate. So we created plate in here. The plate coordination is minus 3.5 by 40, 3.5 by 40, which means the length of the width or length of the raft is 7 meters. And also we have as you see in here, we have 3 walls in a plane strain. So we also draw the wall by the plate as the raft foundation. These are the wall the these are the coordination of the wall. The first wall is located at x minus 2 by 40, and the length of the pile is 15 meter as we mentioned before. So the second point will be 25 meters, and we draw the three walls for a plane strain model. Also, the properties of the raft foundation and walls defined as a plate. So these are the properties of the plate as we calculated in here. The normal stiffness, so the same value as here we used in the PLAXIS, as you can see. Also, these are the properties of the pile. So as we calculated in here, the normal stiffness, the bending stiffness, weight, and we used these values in here. So after defining the raft foundation and piles as a wall, we also apply the surface load to the raft. The surface load is defined in here. Create load, we have point load, and we have create a line load. So because this is a 2D plane strain, it's called create line load, not the surface load. And the amount of the line load we used in this example is 100 kilonewton per meter. Also, we create some polygons in here. As you see, we create some region in here for defining for refining the mesh near the structure. So after that, we proceed to the mesh, and we, in this example, I used very fine mesh because it is a 2D problem and it can be solved in a very short time. So after meshing the problems, we go to the staged construction mode, and we define two we already have initial phase, so we use unpiled raft foundation, and we use piled raft foundation. In unpiled raft foundation, in this phase, we just investigate the we just investigate the raft only under the effect of load without piles. So in the second phase, we activate the pile as well, and we investigate what happened to the settlement and deformation of the raft foundation. So in the unpiled raft phase, we only activate the plate for the raft foundation, and we activate the load as well. In the piled raft foundation, we activate all plates for the raft foundation and plates for the walls as well. Also, the interfaces are activated in this stage as well. So after that, we can start the calculation, as I already calculated, and we can see the result in here. This is first we want to check unpiled raft foundation. As you can see, this is the deformed shape of unpiled raft foundation, and the maximum settlement is about 0.16 meter, which is unacceptable generally in raft foundation. So now we will see the settlement in piled raft foundation. As we can see, it is about 0.03 meter, which is about 3 centimeters, 3.5 centimeters, and it is acceptable. Also, in deformation tab, we can see the contours of the total displacement, and also we can check the maximum axial force for each pile. For example, we can check the axial force of this pile. We click in here, select structure, and double click on this pile. So in here we can go to the force and see in here axial force, and we can see that the minimum value, which is equal minus 294 kilonewton per meter. So this pile also have the same load due to the symmetry, and so I want to talk about the other thing, which is load distribution between pile and raft foundation. As we know, for pile raft foundation, some portion of the load is carried out by the raft, and some portion also carried out by the pile foundation. So the formula is used like that, which is P equal, or rho equal load distribution by piles divided by total load. So we have three piles in a plane strain model, which is three plate, divided by Q, which is the total load we apply to the raft of the foundation, plus weight of the raft times length of the raft, plus number of pile times weight of pile of equivalent. So equivalent means the weight of the plate in meter times the length of the plate. So in this case we see that the weight of the total axial force of this pile is 294, and this one also have the same value due to the symmetry of the example. Also the middle one, we can see it also. It has 155 kilonewton per meter. So we these are the summation of the loads carried by each pile divided by the total load. So it is equal 0.47. What does it mean? It means that about 47% of the total loads are carried by the piles, and the other portion of the load is carried by the raft foundation. Also, I want to say that this kind of numerical model should be used very carefully, because sometimes you may get very unreliable results due to simplifying of the problem, and I suggest that for a pile raft foundation, a full 3D numerical model be used for this kind of example. Okay, thank you for watching this tutorial, and please do not forget to subscribe to my channel, and see you soon in another tutorial.